Welcome everyone to upgrade your fiber optic diagnostics with portable ultra-high resolution optical backscatter reflectometry, a webinar presented by Luna Innovations Inc. and hosted by Photonics Media. My name is Robin Riley and I'm the Photonics Media web editor. I would like to introduce today's presenter, Mr. David Potter, Director of Marketing for Luna Innovations. David will be speaking today on optical backscatter reflectometry and will introduce the Luna Innovations OBR 6200, which simplifies the test, troubleshooting, and diagnostics of fiber optic systems in the most demanding environments. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. All registrants will receive a link to the recording, so if you have a colleague who was unable to join today for any reason, please let them know that this recording link will be available to all. We encourage you to ask questions throughout the presentation. Just type your question in the question box to the right of your screen, and our presenter will respond to as many as possible at the close of the presentation. Also, we will have two short poll questions after slides 4 and 8. And now, with nothing further, I would like to introduce our speaker, Mr. David Potter. Welcome, David.
Thank you, Robin. Yeah, thank you. Let's see, I'll share my screen. Should be good now. So thank you, and thanks to everyone for joining us today. Again, my name is David Potter. I'm with Luna Innovations, and I'm very happy to talk to you today about new developments in the area of fiber optic test and diagnostics. More specifically, we'll take a look at the combining of optical backscatter reflectometry, or OBR technology, combined with a new rugged and very portable form factor that brings this very powerful diagnostic capability to applications in field testing and maintenance, particularly well suited to the more complex, shorter run networks that are becoming more and more prevalent today. Before we dive into that, I would like to give a very quick high-level introduction to Luna Innovations for those of you who are new to Luna. So Luna's been around for about 30 years and is a leader in advanced test and measurement products and solutions based on fiber optic technology. Luna has two main product or business segments. First, Luna offers a suite of distributed and multi-point fiber optic sensing solutions for physical and mechanical measurements using fiber optics. It has lots of systems deployed in aerospace, automotive, and infrastructure industries, to name a few. And then the other part of Luna's business focuses on test and measurement products for customers and markets developing and deploying fiber optic systems and components, primarily for communications. And the technology we're discussing today, of course, falls into this category. Okay, I'd like to start with kind of an overall trend, a very important trend in fiber optic technology adoption, one that's really accelerated and taken off in the last 20 years or so. So while originally fiber optic networks were exclusively used for long-haul networks, however, starting in the 90s or so, the explosive growth in our hunger and demand for data and bandwidth has really driven the adoption of fiber optic technology because of its superior speed, its capacity, and low power consumption into more and more applications and more replaced copper in these wide areas. And so it's pushed into all areas of networks, in the local area networks, into data centers, aircraft, ships, factory floors, industrial equipment, and so on. And now even circuit boards are using fiber optics and optical components for high-speed interconnects and for on-chip processing with kind of the development of integrated photonic circuits. So with this, of course, kind of our byproducts of this is that more and more networks that are in this kind of short to medium range are becoming more and more prevalent. So as this rapid this rapid adoption and expansion of fiber into these shorter range applications do bring with it some unique testing and maintenance challenges. So in these shorter installations, for example, and I guess obviously network components are closer together and more dense. Also, the nature of many of these deployed applications means they could be very difficult to access different parts of the network or the fiber optic assembly that's embedded and deployed in the application. And also, again, by the nature of many of these applications, downtime is very expensive for testing and maintenance operations. So obviously, proper installation is even more critical than normal, and testing, diagnostics, and troubleshooting just has to be as fast and efficient as possible, especially for these short range and medium range applications. And so actually, this is where we'll pause and have a quick poll question for you.
Okay, thank you, David. And I'd like to take a few seconds here and launch poll question number 1. And the question is, what is the length of the fiber optic assemblies networks with which you regularly work? Check all that apply. And the possible responses are greater than 10 kilometers, greater than 1 kilometer to 10 kilometers, 101 meters to 1 kilometer, 51 to 100 meters, 50 meters or less. I'll give you a few seconds to respond. Okay, thank you, everyone. I'm going to share the results quickly. And 19% said greater than 10 kilometer, 25% said greater than 1 kilometer to 10 kilometer, 27% said 101 meter to 1 kilometer, 25% said 51 to 100 meter, and 69% said 50 meters or less. Thank you. I'm going to hide the poll and we'll go back to our presentation.
Okay, thank you, Robin. And yeah, thanks everyone for that poll. It's very interesting. It looks like pretty evenly distributed, and there are a lot of attendees with short networks. So that's a good thing. So as one of the example of shorter network lengths, let's consider the deployment of fiber optic networks in a modern fighter jet. So fiber optic communications are critical for the performance and operation of these very advanced aircraft. In these systems, the deployed networks and links are relatively short, usually on the order of tens of meters. You have multiple sections and connections. Sometimes these sections are on the order of 1 meter, so very short. An important aspect of these networks is their restricted access. So while some type of maintenance port is typically provided in these systems, assessing other parts of the network for diagnostics reasons or replacing a faulty part, as you can imagine, is extremely costly. And of course, then in terms of the environmental conditions, the diagnostics and the troubleshooting and the repairs happen out on tarmac, so the conditions can be less than ideal. So as you can imagine, the fast and efficient diagnostics is a requirement for these applications. The ability to quickly and very precisely detect faults and issues and determine the exact location, the very precise location of the faults is extremely valuable in these types of applications. So let's maybe take a step back and look at some of the more standard approaches to fiber optic test. I'll look at a couple basic approaches. This first is, simply if I have a cable assembly I need to test, one of the more basic ways, other than something like a visual fault locator, is to connect a known light source to the fiber optic assembly and use an optical power meter to measure the amount of light coming out of the fiber, giving a measure of the overall transmission loss. These two functions are often packaged into a what's called an optical loss test set. This approach is very simple and basic, which is a good thing. However, kind of the two main challenges or shortcomings with it is, one, we require access to both ends of the fiber assembly, and also it just gives us the total transmission and the total loss. It doesn't give us any indication of where in the assembly the problem would be, what section of this assembly needs to be addressed. And by the way, sometimes these do include functions for return loss as well. So the next kind of step up is also a very popular and well-known instrument. That's the OTDR, which stands for Optical Time Domain Reflectometer. So the OTDR probes a network with a pulse and delivers a trace of reflection versus length along the fiber. And the magnitude of the reflection kind of tells you where connectors or where the problems are in the fiber optic network. So the OTDR does address the issues with the optical loss test set. It gives us location information in terms of locating where an issue is and where we're having lossy events. And it does only require a single point of access because it works in reflection. So the OTDR is a long staple of testing fiber optic links, particularly longer networks that are can range tens or hundreds of kilometers in length. Now, for these shorter networks that we're talking about today, however, like these 50 meters or less networks, spatial resolution of these OTDRs is a real limitation. So when you're testing a 10 kilometer or 100 kilometer fiber network, identifying a fault within a meter or two is extremely useful. But when identifying the exact location of a fault in an avionics network that's only 20 meters long, you really need to know, and it's very valuable to know, which section, which connector has an issue, which side of a cabinet or which side of a bulkhead the problem is on. So we'll be talking about some more about using reflection to test fiber optic cables. So step back for a second, just cover some of the basic terms and concepts. So in a fiber optic system, we classify reflections into two categories. The first is discrete reflections, referred to as Fresnel reflections. So this is caused when light traveling down the core of a fiber encounters material with a different index of refraction, indicated here in a figure with the letter N. This causes a reflection of some portion of the light. This could be a fiber core hitting a air gap. It could be two fiber cores with different materials spliced together. And so examples of these discrete reflections are connectors or mechanical splices in a optical fiber. The other type of reflection is distributed reflection in the form of what we call backscatter. And in standard optical fiber, the dominant form of backscatter is Rayleigh backscatter, which is caused by minute variations in the density of the material of the core that just naturally occurs. And so what you get is a very low level backscatter reflection pretty much continuously along the fiber optic cable, along the fiber optic core. And this Rayleigh backscatter, as we'll see, is a very important tool for measuring loss along a fiber. Okay, and then one more slide on some of the basics of testing fiber optics. So for quantifying loss in fiber, we use the parameters return loss and insertion loss most often. So return loss is a measure of the reflected light and is a ratio of the reflected power over the incident power, which kind of think of it as reflected power versus the input power. And we usually express this in terms of decibels. And so 0 dB would correspond to 100% return loss. Example values of return loss for some common connectors are shown here, and values vary, of course, but we can see that an APC connector pair would typically have return loss of somewhere in the neighborhood of -65 dB, while an open flat polish to air interface would be much brighter at about -15 dB. And if you're, I guess if you're thinking in dB is not second nature to you, kind of added the percent number there corresponding to the dB value. Now, insertion loss, on the other hand, is the ratio of the transmitted light to the incident light, also expressed in dB, and we tend to use the negative notation for this as well. And so in this case, 0 dB, again, would mean 100% of the light was transmitted without any loss. So lower numbers are good. Again, and again, on the lower right, some typical insertion loss values that you see for a connector pair, 0.2 dB or less, as well as for fusion and mechanical splices. Okay, and I think this is where we wanted to ask another poll question about your usage of fiber optic test tools.
Thank you, David. And we're going to go to our second and final poll. And our question here is, what test tools are you currently using for FO testing and diagnostics? Check all that apply. The possible responses are visual fault locator, optical power meter, optical loss test set, IL or RL, OTDR, OFDR/OBR. I'll give you a few seconds. Okay, thank you. I'm going to close and share the responses with everyone. So 46% said visual fault locator, 69% optical power meter, 33% optical loss test set, IL or RL, 52% OTDR, 33% OFDR/OBR. Thank you, everybody. We'll go back to our presentation now.
Okay, great. Thank you, Robin. Yeah, it's really interesting. You know, obviously, most of you are using multiple test instruments, and it's not surprisingly optical power meters, very popular, as well as OTDRs, and a pretty good distribution among the other ones. So speaking of OTDRs, let's kind of go back to the OTDR and talk about that, because you know, this is the type of tool that we want to talk about with OBR. So an OTDR, again, works by launching a light pulse into a network and capturing the reflections, you know, both the discrete reflections from the connectors as well as the distributed deflection from the relay backscatter. You know, I'm going to grab my laser pointer here, and so here you see we have the peaks from reflections from the discrete reflections, and then kind of this baseline level is essentially our backscatter reflection. And as we'll talk a little bit more in a minute, the decrease in that relay backscatter indicates the loss in the you know, in the fiber itself. So yeah, so the OTDR, again, so using these methods, it can measure return loss and insertion loss at different locations along the fiber. And again, it's a very good tool for diagnosing fiber optic networks. However, for these short haul network applications, again, the resolution of the OTDR becomes an issue. And that has a lot to do with this concept called dead zones. So an OTDR dead zone tells us essentially how close two reflections can be detected and measured. And there's actually two types of dead zones that are specified for OTDRs. An event dead zone indicates a minimum distance that two consecutive reflective events can be detected or distinguished, but not necessarily measured. And then the attenuation dead zone basically is determined by when that trace returns back to close enough to the backscatter level where we can accurately measure the amount of loss, because again, we use that backscatter level as kind of our baseline for our loss measurements. So the actual dead zones of OTDRs in practice will depend on many variables of how the OTDR is set up and configured, and also the size of the reflection. For standard OTDRs, you're typically in the range of 1 or 2 meters or so. There are some specialty high resolution OTDRs that do have better or smaller dead zones than this. Seeing them specified around 20 to 40 centimeters. But again, keep in mind that it does vary on a lot of variables in different settings, and also reflection. So higher reflections can actually cause more saturation of your OTDR, which will drag out that dead zone even further. So that brings us to OBR, or Optical Backscatter Reflectometry. So this is a tool that measures distributed loss, very similar to an OTDR, but with orders of magnitude higher spatial resolution, so that you can see much more detail. You don't have to deal with these types of dead zones, and precisely locate and qualify all the issues in your shorter networks. So optical backscatter reflectometry, or I'll try to use the term OBR mostly from here on out. So OBR is, again, a measurement technology that, again, delivers data similar to an OTDR, reflection versus distance, and we can map out both discrete reflective events as well as distributed reflections and backscatter along a fiber optic assembly. Features ultra high resolution. So OBR products are available now with spatial sampling resolutions as low as 10 micrometers. There's no need for a launch cable. We start measuring it right at the connector of the instrument. Very high sensitivity so that we can detect backscatter even at high resolutions. And with that high sampling resolution, we have the ability to make very precise latency measurements as well. And so here in this example, why this looks on the surface like an OTDR trace, we can actually zoom in quite a bit, and the detail is there to see that even within a connector pair, we can look at different components within the connector and differentiate between the actual connector face reflection and, say, a bad splice right at the base of the connector. And we'll see some more examples of that. So optical backscatter reflectometry, or OBR, while OTDRs are based on time domain measurements, OBR is based on frequency domain measurements, and more specifically, optical frequency domain reflectometry, or OFDR. I won't go into much detail, but just at a very high level, in oversimplification, I'll explain quickly the kind of basic concept. So OFDR is an interferometer measurement method that uses a very specialized, very finely tuned swept wavelength source. So this swept wavelength light is sent to the device to be measured. So that would, here, we have the two reflectors. We think of that as the device we're testing or measuring, and the swept wavelength source is also sent through a reference pass. So the reflections from our fiber that's being tested is then combined with our reference signal, and the result, to combine those two signals, the result is basically a beat frequency or beat frequencies, and we create frequencies that are proportional to the distance or the time delay based on how close or far away those reflections are from the combination there. This all gets summed up. Show that. This all gets summed up and transformed into a frequency domain data, which maps directly to the measurement or time along a measurement path. So this OFDR is a general technique, and Luna has for many years kind of refined and improved and augmented this approach, and And that is what optical backscatter reflectometry is. It's essentially a very evolution of OFDR technology. We've deployed OBR based on this OFDR in several products, and these products are widely used in a variety of fiber optic test applications, whether on the manufacturing floor or in the R&D lab. And what we wanted to introduce today is bringing this OFDR technology into a new portable and rugged and transportable platform. So the OBR 6225 is a new portable OBR. It has the ultra high resolution of OBR, ultra high sensitivity, and that is packaged in a way that is ideal for field maintenance applications for fiber optic systems and networks. It's a battery powered, rugged, and very easy to use system. And I'll give you some examples of that. Here are some specifics on the product in terms of what it's capable of for your reference. So we offer a couple different versions with 1 or 2 channels. The actual spatial sampling resolution is 80 micrometers when configured for the 20-meter range, and that does increase a little bit as we go out to 100 meters with a 200 micrometer range. But again, we don't have the additional dead zone issues, and our real event resolution is simply twice that sampling resolution. This instrument scans at the C-band and has a very high sensitivity of a -129 dB. So the ability to see very small reflections. And of course, as we'll see, it's distributed RL and IL measurements, and including the ability to do automatic reflection loss event detection and location. We put a lot of effort into making this system as easy to trouble-free to use and operate, and so a big part of that was implementing automatic self-calibration and optical alignment. So there's no external connections or anything needed to start up the system and start taking measurements. We offer a version which is IP65 rated, which means it's very water resistant, as well as dust proof, and with Ethernet and USB connectivity. I'll show some more examples of this in a second, and actually a demo here in a second, but this gives you an idea of the interface. I wanted to orient you to this. So again, this is the main screen on the OBR 6225. We have essentially the reflection versus length, and there on the right, you see we're showing the automatically detected event table. So you can set up, the user can input different threshold values and parameters, and the system will automatically detect loss events. So wanted to also talk a little bit about how we calculate return loss and insertion loss, how we quantify that. So if we zoom in, there we go. If we zoom into one of these reflection peaks, so this happens to be a bend, I think, but in general, this could be a connector gap or any type of discrete reflection event. Before and after that event, we have the kind of that baseline Rayleigh backscatter reflection that we see there. So the way we measure and quantify return loss is we simply integrate, shown here with the green line, we integrate over the peak and to measure and integrate the amount of light that is reflected. So that gives us our return loss. And then insertion loss is just looking at the decrease in the Rayleigh backscatter before and after the reflection event. And that will give us insertion loss. So this is, a lot of you have used OTDRs. This is very similar and essentially the same type of approach with quantifying RL and IL with OTDRs. Okay, so now let's want to get to I don't have a live demo, but I have a video of a live demo of a test of a simple assembly here. So we have a couple multi-mode fibers, jumper fibers concatenated We also have a multi-mode conditioner here to essentially, so we propagate all the modes evenly in the multi-mode fiber. And then we do have a simple single mode termination cable there at the end as well. So I'm going to switch over to a video, and we're going to kind of see how the 6225 operates, and you get a sense of the user interface and working with the instrument. So this is, we've not scanned that network yet. We've actually scanned just the adapter cable. So this is the assembly I just talked about. Here's the mode conditioner. Here's the two multi-mode fiber cables. And now we'll connect it up to the OBR. And then we'll take a scan of that assembly. Again, only touch screen, so we have the large fingers in our screen here. So here is a trace of again, reflection versus length. And we'll kind of demo how you can interactively zoom in, as much as you want. Essentially what we're seeing here is, this section here from about 1 to 2 meters is our multi-mode conditioner, and that's the actual conditioner there with that drop in insertion loss. And here we're measuring it with a single cursor. So the software allows you to interactively pick a peak and calculate the return loss at that location and the insertion loss. So here we see it's about a little less than 3 dB insertion loss with that mode conditioner. Over here to the right of that are the two multi-mode fiber segments here. And these peaks, of course, are the connectors, the PC connectors for those multi-mode fibers. So now we're going to turn on the event detection. So in this menu, we can set the thresholds for loss as well as the integration parameters for calculating return loss and insertion loss. Close that out, and you see the table shows up here on the right, and there's our detected events. We can scroll through those events, and highlights those. And you can see the calculated values for return loss and insertion loss at each event. If you double click, it automatically zooms to that event. It can be a useful tool. Okay, so I'm going to turn the event table off, and we're going to introduce just another fault, if you will, in the fiber. I'm going to put a tight little bend there right next to the second multi-mode, the connector on the second multi-mode fiber. We'll scan it again, and if you look here around 3.3 meters, you see that reflection peak here. That's from that bend. Right there, pretty close to that connector. We'll get our cursor again so we can measure the amount of that loss with that bend. And measure return loss as well as insertion loss. And then we can also measure the location. So we have 6225 has a variety of cursors available. Pick the vertical cursor. We can automatically calculate the distance between the two cursors by aligning it on the two peaks. And there we see that our bend is about 9.1 centimeters away from that connector face. Okay, so that's hopefully that gives you an idea of how the OBR 6225 operates and what the user interface is like. I'd like to maybe show just a couple more quick examples and a couple more measurements to give you a more full idea of what the product's capable of. So here, a simple test of a short single mode fiber, a jumper cable. It has a pinch in it, as well as we'll see, a bad connector. So here I don't have video, just a screenshot. And so this is the trace resulting. So you can see here we have about, should have pointed this out earlier. So here it's 0 meters. So that's the front connector of the instrument. here at a little over 1 meters. That's the end of the adapter cable. So our actual jumper cable starts at this point, at this reflection. That's our connector. Here's our bend, it's labeled, and here is that terminating, or that end connector that's just open to air. Okay, so that's great. We can see a large reflection from that non-terminated connector. But if we zoom in to that connector, this kind of shows some of the detail that you can see with the OBR. So this connector is actually, if we zoom in, we actually see 3 peaks. So the first peak is a crack in the fiber at the end of the ferrule, and then the next peak is the opened face at the end of the ferrule, so the fiber at the end of the ferrule. And then we're actually seeing a third reflection there from the cap that's on the fiber ferrule as well. And so I could zoom in. Actually, I do zoom in a little bit more here, and again, just for fun, measure the difference from that crack to the end of the ferrule, that open face. Looks like that's about 9.2 millimeters. And we want to know how tight our cap is. It shows us that our cap is about 3.8 millimeters gap from the end of the fiber optic. All right. So I want to talk about one other application with the OBR, and that's the measurement of latency and time skew, or length, in fiber optics. Again, because we have this very high resolution sampling of loss along a fiber, we can use that to make very precise measurements of latency along a fiber. Because that's essentially what we're measuring, is how much time for light to travel through a flight path, in this case a fiber optic cable. This can be very interesting for a number of applications. So in high-speed trading, in financial data centers, in financial centers, where the latency is regulated, this becomes important. Manufacturing quality control, if you need to check the length of a fiber, delay lines, phase array radar, where again the length of the fiber is critical. We can check that and test that with an OBR product. So with the OBR 6225, this table here shows what kind of accuracy we see with that portable instrument. And so this is our accuracy for measuring the latency. If we're in the 20-meter mode, it's 5/1000ths of a nanosecond. So fractions, very small fractions of a nanosecond type of latency accuracy that we can see in much higher resolution. And that corresponds to, see there, less than 1, 2, and 4 millimeters in terms of length accuracy. You kind of, to show you an example of this application. So here we have a multi-fiber cable that has 4 fibers in it. So here we connect the OBR through a jumper cable to a 1x4 splitter. And then we're looking at the reflections from all 4 fibers. So in order that the reflections don't come back on top of each other, we stagger each of the 4 leads by about 20 centimeters, so that we can discern the different reflections coming back. So if we scan this, this is what the trace looks like. So again, here we have our splitter, and as you expect, there's a decent amount of light lost there, but yeah, but here is the, over here are our 4 connectors corresponding to those first 4. Here are the second group of 4 connectors. Now, if we measure kind of the difference between each pair, we see that we can make some very, very accurate, very precise length measurements. Here we're expressing it in terms of meters, and we have looks like the biggest difference between any 2 is about a little less than 15 millimeters. Okay. So, I mentioned that Luna has developed a number of OFDR products, and the OBR 6225 is the latest kind of addition to this family. So yeah, we have other optical backscatter reflectometers. 4600 is really our workhorse these days. It delivers the highest level of spatial resolution down to 10 micrometers, sampling resolution, and also has a lot of some additional measurement features in terms of tracking polarization and phase measurements. And then also based on OFDR, we have the optical vector analyzer. So this is more of a full parameter characterization instrument. Is used usually with components. So we can do a complete characterization of optical components using OFDR, including full polarization analysis with a single scan. And then the component analyzer, the 6415, also is geared towards components as well. It includes OBR functionality, but also can measure systems in transmission as well. It is very focused on making IL and RL measurements, and is well suited and very fast and streamlined for manufacturing applications. Okay, so that kind of brings me to the end here. Right, again, the main message, of course, is that OBR opens up a new class of OTDR-like measurements to give you the resolution and the sensitivity that's very valuable for the shorter networks, such as you find in aerospace and other deployed types of applications. And now now that functionality is available in this battery-powered portable form factor for maintenance and field test applications. So with that, I'll turn it back over to Robin for, I think, a Q&A session.
Thank you very much, David. And attendees, if you have any questions, please enter them into the questions box to the right of the screen. And Luna Innovations will receive a copy of all of your questions, and they will create a Q&A document with their responses to your questions, and they will be sharing that document with all registrants. So we have many questions here. We may not be able to get to all of them, but please don't let that discourage you from not sending in a question, because it will be answered. So we'll begin with our first question here, David. What happens with few modes fibers?
Okay, so I think, I guess I'll assume you're asking about multi-mode fiber. So yeah, I'll talk about using multi-mode fiber with the OBR. So the OBR, the interface to the OBR is single mode. So that's why in the demo example, we use a multi-mode conditioner. Now you can kind of have two choices. You can launch single mode fiber directly into a multi-mode fiber, so you can directly connect it. You will still see the reflection events. The length will be accurate. The location of the reflection events will be accurate, and is typically just fine for most diagnostic capabilities. If you do want more quantifiable data and actually more accurate RL and IL measurements, then you would use a mode conditioner. And what the mode conditioner does is essentially populates, kind of evenly distributes the modes into the multi-mode fiber, so that the our measurements of RL and IL are more accurate.
Thank you. Next question here. How would you increase the resolution down to 1 to 10 if the measurement distance was fewer tens of centimeters? Was few tens of centimeters.
Yeah, so that's yeah, kind of, that would be a something that we would have to implement into the product. That's not something that's a feature for the product. The the sampling resolution is really driven by the scanning range of the laser, and so we're able to scan wider wavelength range. We'd be able to get lower resolutions. We do, as I mentioned, we do have products which do get lower down to 10 micrometers. And actually, the 10 micrometers spec is for kind of in standard fiber. If you, that's assuming a certain index of refraction. It's actually less than 10 micrometers for a, so for a different index of refraction, say in a silicon photonics waveguide. So yeah, I think basically it would require kind of a retuning and reworking of the OBR instrument. It's not impossible, but it's just something we haven't done.
Okay, thank you. And here's our next question here. Will this unit work on single mode fiber as well?
Yeah, absolutely. Yeah, and actually 2 of the examples I showed were single mode fiber. So yeah, as I mentioned, it launches the interface to the OBR is single mode fiber. So yeah, no problem whatsoever with using single mode fiber.
Thank you. Our next question here. OBR 6225, does it allow you to measure in real time? Or is OBR 6225 only a single scan mode?
Okay, yeah, that's a good question. So yeah, the way the OBR 6225 operates is in a single scan mode. So you saw in the demo, perhaps, click the measure button, it takes a single measurement. So it is not in a continuous, we call it continuous mode where it's constantly taking measurements as fast as it can. We do have other benchtop instruments, I mentioned the 6415, where we're measuring there at 6 to 12 times a second. You can put it in continuous mode and we're constantly taking those measurements. But yeah, with this portable system where we have a lot less computing power, basically it's a single measurement per button push.
Okay, thank you. The next question here. He says, thank you for the presentation. Does the OBR 6225 also enable the calculation of distributed strains as in OBR 4600?
Okay, yeah, another great question. Yeah, and I guess for the rest of the audience who may not be familiar with the OBR 4600, so that's another OBR from Luna that, in addition to making these types of measurements that I showed you, can also be used with some software, some additional software processing of the relay backscatter can be used to measure strain and temperature. And so we have that product, and we also have a dedicated sensing product that really optimizes kind of the same technique, but for strain and temperature. So with the OBR 62, having said all that, the OBR 6225 itself does not support strain or temperature measurements currently. Yeah, it's really for fiber optic testing, RL and IL, but yeah, I guess you could stay tuned. I think that would make a lot of sense to have that capability sometime in the future.
Okay, thank you. And our next question here is, how did you measure the accuracy of OBR?
Okay, that's a pretty broad question. So I guess when we specify, I assume you mean when we're specifying the accuracy of the OBR, we not only measure the specification, but also prove out the theory and determine what is the worst case accuracy that we support. Yeah, I honestly don't know the specifics of exactly how we measure it. I do know that we have onboard calibration to kind of help us maintain that accuracy. So, for example, we use a gas cell to calibrate and maintain our accuracy of the wavelength, so that as we're scanning the system, it's as accurate as possible. So, yeah, I think, yeah, we'll have to. I'd have to get with our engineers and get a little bit more detail of how we do that, and we can include that in the Q&A write-up.
Thank you. And excuse me, attendees, you can also email your questions into either David directly or to the solutions email address on your screen. So here's our next question, David. Can the OBR 6225 test EM fiber?
Polarization maintaining fiber, yes, it can. There's no problem with that.
Okay. And our next question here is, what is the difference between slicing and splicing of optical fiber?
I'm not sure. I guess I'm not familiar with slicing. Maybe that was a typo or something. But yeah, splicing obviously is splicing, joining two pieces of fiber. So yeah, I'm not sure what slicing is. Perhaps that was a typo.
Okay, and I'm not that familiar with the product, so it could have been a typo on my end as well. So our next question here is the instrument in production now?
Yes, it is. Yeah, the OBR 6225 is in production. We're shipping these. Have shipped several of the two different versions. Yeah, and I mentioned here, kind of in this slide, you can see again we're offering two versions. One is IP rated, and one is not. It has a more standard connector. To get the IP connection, we need a IP rated connector, and so that's the large black connector. So both of these models are in production now and are available.
Okay, thank you, David. And here's another question for you. Using the Ethernet interface, what is the refresh rate that could be obtained from an offsite technician's access to the unit?
Okay. Yeah, I'm not sure. That's yeah, I'm not sure what the rate would be. I'll have to check on that and get back to you.
Okay, and attendees, as we mentioned, we will be sending all of these questions to Luna, and Luna will be responding to your questions. Okay, so our next question here: what is the IL and RL resolution of the portable OBR unit versus the OBR 4600?
Yeah, I have the. So I have the numbers. I don't have the 4600 right in front of me, but the I can tell you that the resolution of return loss for the portable unit is 0.1 dB, and for both, and that's actually both for return loss and insertion loss. And I believe that's comparable. Like I said, I don't have it in front of me, but I believe that's comparable to the 4600, but I'd have to double check.
Okay, thank you. And here's more of a general question. Which is better, time domain or frequency domain reflectometry?
Well, I have a biased opinion about that. And it's serious, that's kind of what I talked about. They're two different technologies that are really optimized for two different applications. Time domain reflectometry, works great for long distance, obviously because it's the tool of choice for long distance diagnostics and troubleshooting, because it supports very long networks. Our OFDR can go out to, our OFDR technology and our products, we support out to kilometers, but only to a couple kilometers or so, but not beyond that. So OTDR is really optimized and works well for long distance networks. In these smaller networks, yeah, I think, kind of hopefully as I showed today, OFDR and the OBR technology is a much better fit for these short range networks. And so they're different. They're complementary for different types of networks.
Okay, thank you. Next question here. Are all the products capable of supporting, and he's got minus 129, small d, capital B, power level?
Okay, yeah, the sensitivity or the range, also the range and the sensitivity of the OBR 6225 that I showed is minus 125. Sorry, 129 dB. Our other, our 4600, it's a little bit higher than that. I think it's up closer to minus 140. That's the benchtop OBR 4600 that I had on the earlier slide. So yeah, I think each instrument has a spec for its dynamic range, and in this case for its sensitivity. And this one is minus 129.
Okay, we have a few more minutes here, so we'll take a couple more questions and then we'll close. So the next question will be, if I have a photonic circuit which includes one or more splitters, is it possible to identify the separate paths on the reflected signals?
Yeah, that's a good question, and I guess it would depend on kind of the lengths of the different legs. So if essentially the reflectometry works as you're injecting light into one and looking at reflection from all the different legs. So if the termination of the different paths do not fall on top of each other, then you could look at least kind of the reflection and the endpoint of the different paths in the splitter. So it kind of depends, because you are, essentially looking at data on one channel and overlapping with a splitter. If you have multiple paths, overlapping that data on a single channel. And like in that last example I showed, the way we differentiated those was by purposely staggering the different legs attached on the other side of the splitter, so that the reflections did not overlap. Now, for another option is we do have other instruments such as the OVA, where if you can get access to the other side, you could check out individual paths in transmission as well and look at loss as well as phase and polarization and other parameters.
Okay, thank you, David. And I'll make this one the last question for today. And that is, the question is, how many measurements can be performed per second?
So with the OBR 6225, as you may have seen there, it's basically it's a manual push, take a single scan, and it's on the order of a few seconds. If you saw that, you may have noticed that in the video. I don't remember exactly what the spec is, but it's a few seconds to take a single measurement. As I mentioned, there are other non-portable OBRs and component analyzers we have that are optimized more for speed and can take multiple measurements per second. But with this one, it's a few seconds or so per scan.
Thank you very much. And everyone, thank you for joining us today. A recording of this webinar will be available shortly, and everyone will receive a link to the recording tomorrow in a brief note. I would like to thank Luna Innovations, our presenter David Potter, and all of you for participating in today's webinar on how to upgrade your fiber optic diagnostics with portable ultra-high resolution optical backscatter reflectometry, presented by Luna Innovations Inc. and hosted by Photonics Media. And please don't hesitate to contact Luna if you have any specific questions. Thank you.